Video I will talk about the concept of homomorphic filtering and under what situation we can use the homomorphic filter, and I will show you some examples on which this filter has applied. So basically, for example, if you have an image f of xy and which is formed by two different quantities, let's say I have one thing, let's say f1 of x1 of x comma y and f2 of x comma y, and if these two are two components of the image, let's say this is a low frequency component and this is a high frequency component, then if you want to remove the low frequency component, we will be using a high pass filter. Okay, and if you want to remove the high frequency component, we will be using a low pass filter which allows to pass the low frequency components. All right, but the homomorphic filtering has a different scenario under which we will be using the filter. So if this was the case, that is if there are two different quantities added together and which has two different frequency distributions, then we will be able to apply the frequency domain filtering such as low pass filter or high pass filter, etc. But when an image is formed, just erase this off. When an image is formed, you know that there are two different quantities taking part. The first one is the illumination and the second one is the reflectance. Suppose that if you have a light source here and if you have certain object here and you are capturing that image using some digital image or capturing devices, so it will be getting a light from the light source or illumination from the light source, and this object will have a reflectance. That reflectance will be taken care, and that will be giving you the whatever value has to be reflected onto the photograph capturing surface. So let me call this source as I of xy, that is the illumination coming from a specific point x comma y, and the reflectance of this particular object, let's say it is r of x comma y, and this is small letter I. Okay, and the image that is forming here is f of x comma y. So for an image formation, if you want to get a pixel in the image f of xy, these two quantities are being multiplied. Okay, so they are not added, they are actually getting multiplied. Now suppose it is a situation that this illumination light source has certain problem, or example, or in other words, this is not giving you a proper illumination, and usually these light source are low frequency components. That is, light source, the illumination will have a low frequency. Most of the time it will have a constant illumination over the surface or some variation over the surface. Most of the time it will be a slowly varying frequency component. In other words, this reflectance, usually the object, the way by which we uh, perceive or we visualize different aspect or of the image is through its reflectance. It will be varying to every point to point. So in other words, this illumination will have a low frequency component most of the time. So I'm just drawing a 1D 2D representation, sorry, 1D representation, and the reflectance will be having a high frequency component. So no, this is not being added in the case of a image formation. This is actually getting multiplied. So we will not be, so this will be getting multiplied. So we will not be able to separate out these two things separately as a summation. If you were able to separate it as a summation, then we can apply appropriate frequency domain filtering technique to remove the low frequency component, because we need to remove the low frequency component because we are actually trying to solve the issues that emerged as part of the illumination or the light source from the light source. So what we will do is, so if this is a multiplication function, then we can separate it out as a addition function by finding the logarithm of this particular quantity. So I'm finding a new function f of x from f of xy called z of xy or z of xy as the logarithm of this multiplication, that is logarithm of f of xy. So we know the property of logarithm. The summation will become, sorry, the multiplication will become a summation. So this will be log of I of xy plus log of r of xy. Now what we can do is we can take the Fourier transform. So I will show that. Now what we are doing is we are taking the 2D Fourier transform of this particular function, that is log of f of xy. So we can apply the Fourier transform separately to the illumination part as well as the reflectance part. So I am applying the Fourier transform to the illumination part as well as the reflectance part. Now what happens is, suppose that I am calling this Fourier transform of z of xy as z of uv, and the Fourier transform of illumination as capital Fi of uv, and the Fourier transform of reflectance as Fr of uv. Now what we will do is we will take a filter called h of uv, and we will multiply that h of uv with this function. So what we will get is we will get a new function s of uv, that is h of uv and z of uv. Okay, so we will get two different parts. One is multiplied, the h of uv is multiplied with fi of uv, and h of uv is multiplied with fr of uv. So what essentially happened is I told that we have a multiplication function, and if you take the logarithm, so this will be the output after taking the logarithm. That is, this will get some different changes depending on the logarithm function, but I'm just plotting it as it is. You just have to keep that aspect in mind. Now I have the reflectance part, so that will be a high frequency thing. Now what I am doing is I am finding H such that H is a high pass filter. So you can imagine a high pass filter. So if you have a high pass filter, what will happen? So high pass filter is something that passes if all frequencies above a certain level. Okay. Now what will happen? So I am multiplying this one with this one and this one with this one. Okay, these two are multiplied together, and this function and this function are multiplied together. So that is what is written over here. That is, I am multiplying h of uv with fi of uv and h of uv with fr of uv. So you can see that this thing, that is the illumination part, will be eliminated because you will be multiplying this one with 0, and there is nothing to multiply a non-zero value after this particular point. And in this case we do not have anything below this frequency, and we will be keeping all the frequencies after that. So essentially this will be giving you this is summation, that is you are multiplying here, you are multiplying here and taking the sum, and essentially this will be giving you a final output which contains only high frequency part, but this high frequency part is in logarithm domain. So this is the that is, you can consider this SU of S of uv as this particular graph. Now what we have to do is we have to take the Fourier inverse. So we will be taking the Fourier inverse of this one, S of uv. So you are applying this to separately to the two different functions. Now you have the Fourier inverse of Ix of uv, I dash of xy, and r dash of xy. So I dash of xy will be uh, something like 0. That is, I dash of xy will be the inverse after multiplying this factor, and r dash of xy will be the inverse after multiplying this factor. Now what we have to do is so this is actually in the Fourier domain even after taking the Fourier inverse. Now what we have to do is we have to invert the logarithm operation. So we can invert the logarithm operation after taking the exponential operation. So you are applying exponential operation with the function s of xy. So that will be can be separately applied to r of xy and er of xy. So you will get I0 of xy and R0 of xy. So this is the final image that you are getting, I0 of xy and R0 of xy. So I0 of xy correspond to e raised to I dash xy, and R0 xy correspond to e raised to R dash xy. So in this image summarizes the whole procedure. So you have f of xy as a product of illumination and reflectance. You are taking the logarithm, so you are separating that into a summation. Then you are finding the DFT, that is you are converting that into frequency domain. Then you are appropriately applying a high pass filter. Then you are taking the For inverse, then you are inverting the logarithm operation, then you are getting the output result. And here I am showing a graph which is typically used to for the homomorphic filtering applications. So this actually takes the shape of a hyper. You can you can actually approximate this to the shape of an ideal high pass filter. So ideal high pass filter something like this. And in order to avoid the ripple effect due to the Gibbs phenomenon, we are usually using a gradually increasing function which is given by the different functions such as the Butterworth filter or a Gaussian filter. So this is one of the filter that we can use, that is given by this equation. So this equation, you can see that this e raised to minus c d square uv divided by d0 square is actually the Gaussian function. If you subtract it from 1, this is actually a Gaussian high pass filter. Then you are scaling to a level which is actually given by gamma h minus gamma l. Gamma h minus gamma l is this one. This function will have a maximum magnitude of 1. So if you multiply that with gamma h minus gamma l, you will get a value that is within this range, or magnitude with this range. Then if you add it with gamma L, that is, you are actually adding this one with gamma L rather than starting from 0. So you can push the lowest level to gamma L and the highest level to gamma H. And you can imagine such a function with this form, that where the center value has a very lower magnitude, so that will be represented by a dark pixel, and it is increasing as you go from the center. That is, you can correlate with this graph. And here I will show finally a example which is uh, where we are enhancing the image, or we are actually getting the correct visualization of an image using homomorphic filtering. So when you consider the first image, this image has a problem. Actually, this image is not properly illuminated. You can see that the illumination is a bit less at this corner, but it is a bit more in this corner. This is actually happening due to the fact that the illumination was not proper. So the light source which was uh, incidented on the image that we are capturing, this is actually an image that we got through a microscope. So the illumination was not proper. So here we have a very poor illumination, but it is a bit more at this side. So what we will do is we will just remove the effect of illumination. Then you can see the correct image without any distortion that happened due to illumination. So when you look at this picture, there is no illumination variation at this corner or at this corner. This is normally illuminated, or it is illuminated without giving any artifacts that generated due to the problems of a light source. So this is the way by which we can remove the problem that had happened due to the improper illumination while capturing an image. So we can use homomorphic filtering in such situations.